Yeah, very good morning. Yeah, today now I am going to discuss about LED configuration. In last class I already discussed about what is LED, what is the basic principle of LED, and how many characteristics, the characteristics of LED I already discussed it in last class. Now that last class continuation, this is LED configuration. Today now I am going to discuss about that is LED configurations. Okay. Now here there are the two configurations are there in LED. What is the two configurations? First one is that is what is the surface emitting LED and edge emitting LED. It is also called as the surface emitting LED. That is, it is also called as SLED. That means surface emitting LED, and edge emitting it is also called as ELED. That means edge E means that is edge emitting LED. Okay. Now depending on this, now we have to now the next one is that is first next one is uh, first one, that is surface emitting LED. In the surface emitting LED, how the structure is there? In this surface emitting LED or that edge emitting LED, what are the materials we are using? I already discussed in last class. What are the materials? Silicon, gallium aluminum arsenate or gallium arsenate, gallium aluminum phosphate we are using. The materials we are using in LED to further when we are fabricating this particular LED, we are using these materials. Okay. Here surface emitting LED. What is the surface emitting LED? This is the symbol of surface emitting LED. Here when that means the symbol for the LED, the arrow this indicates light is given off. Okay, that light is given off. Okay, this is in the surface emitting LED, or it is also called the front emitter LED. Front emitter LED. This is nothing but what is this? This is a fiber. Okay, na? And this is circular well. That is what is this? Etched well and bonding material and metallization layer. This is, and this is substrate. Okay, na? Now here this is the nothing. This is actually this is our active medium. That the substrate now I am using for the silicon dioxide isolation. The substrate now for that to joining purpose, the isolation, that is silicon dioxide isolation now I am using, and circular metal contact. This is one circular metal contact to join the different materials. Okay, this is surface emitting LED structure. In the circular emitting LED, surface emitting LED, how the output we are getting in the circular surface emitting LED, the output is in the form of lambert pattern we are getting output. Okay, na? Plane of the active light, that is the plane of the active light emitting the region perpendicular to the axis of the filter. That is the region, the output light we are getting in the region that is perpendicular to the axis of the fiber. Fiber cemented into well. That fiber is cemented into that particular well. Okay, na? And active region approximately, that is the region of the active medium region, the length is that is 550 micrometers diameter and 2.5 micrometer of thick. Okay, na? And emission pattern isotropic with that 120 degrees half power beam width, and Lambert patterns we are getting that pattern of beam output, light output we are in the form of Lambert pattern. Okay, power decreases as cosine of theta. That means depending on that angle we have to decide that how much of that brightness of the particular LED. If suppose the angle of that the angle is there, incident angle is there, that angle, if it is less angle is there, the brightness of the particular light LED is very light, that means light, okay na. And coming to that, if it is when we are increasing the theta value, we are getting that more brightness output. Okay, now source is equally bright when viewed from any direction. Okay na, because it is the, if it is we are increasing that theta, then we have to view that particular output beam in any direction. Okay, as projected area decreases as cos theta. Okay na, the cos theta, that means cos theta value when we are increasing the projecting area, that means the direction, it will glow very less amount of the area. Okay na? That is. And coupling and coupling not good and health divergent. These are main characteristics of surface emitting LED. Coming to this next one is, that is edge emitting LED. In this edge emitting LED, here surface emitting LED is a homojunction type of the LED. Coming to this edge emitting LED, this is the double heterojunction LED. Okay na? Double heterojunction LED, because here in this double heterojunction, I already discussed, there are the more than two layers are there, more than two layers are there. The materials which we have to fabricate the particular edge emitting LED are different materials. Okay na? The output, where we are getting that output, in this only one edge we are getting this output. Okay, this is the structure of edge emitting LED. Okay, here this is one layer, this is one layer, this is one layer, here also one layer, here and top, and in this top of this LED we are coated with one layer, that is to reflect the light purpose, we are coating this one thick layer. Okay na, here in this portion only we are getting some light. Edge emitting LED. In this edge emitting LED, active region, that means whatever that active region is there, that is in the form of a the active region is the active region refractive index, whatever that refractive index we are getting, that gradient side layers. From wavelength channels, the direction optional radiation towards side into the fiber. Active region is, that is 50 to 70 micrometers wide, and the length is there, that is 50 to 70 micrometers wide and 100 to 150 micrometer long. Okay, and emission pattern, how we are getting that support output emission pattern in the Lambert pattern with that 120 degrees of horizontal direction. There in surface emitting, in perpendicular direction we are getting. Okay na, that is the only difference. And when proper choice of wavelength, thickness, it can be 25 to 30 degrees vertically and better than surface emitter. The output is we are getting that more than surface emitter, but construction is very complicated. This edge emitting LED. And radiance and emission response time. How the radiance is there, how that emission response time is there. That decides how the radiance is decided. Radiance, that means that is the brightness. Okay na? It measures in watts of the optical fiber radiated into a unit solid angle per unit area of the emitter surface. And one more thing is, that is high radiance necessary to couple the sufficiently high power level into a fiber. This is radiance. And emission response time. What is that emission response time? That time delay between application of the current pulse and the onset optical emission. That is nothing but emission response time. By using this, we have to measure that response. We have to measure how much of that output we are getting on that particular LED. Okay, output optical output, that means LED output. Here this is the current versus light output, output for that surface emitter LED and edge emitter LED. In this less amount of that output we are getting in edge emitter, and the higher amount of that output we are getting in the what is the surface emitter. Okay. Next, and modulation capability of LED. What is how we can modulate the, if suppose any LED output is, if it is the intensity of the light is very less. Now I want to get that higher intensity. Now how we can modulate capability of the particular LED? By using light output from LED can be modulated by wide band information signal, and response time is always greater than 1 microseconds and sufficient for common applications, not suitable for communication application, as response time required that is less than 1 nanoseconds, and modulation capability restricted by, first one is diffusion capacitance, and next one is practice diode space charge capacitance. By using these two, we are capable of the restricting the modulation. Now, frequency response of LED. What is the frequency response of the LED? The frequency response is entirely determined by the diffusion capacitance. If we calculate the diffusion capacitance, that is directly proportional to the frequency of LED. It can drive the current is modulated by the frequency of omega, that is nothing but omega. Output optical intensity is measured by using current, that is this equation. I of W is equal to I naught into 1 plus omega T efficiency square all to the power of minus 1 by 2. By using this, we have to measure the optical intensity. Okay, na? I naught is intensity emitted at 0 modulation frequency, and tau efficiency is effective carrier lifetime. By using this equation, you have to measure the output intensity of the LED. And what is this output? Optical output bandwidth. The optical output bandwidth, this is that for the optical output bandwidth for voltage spectrum and the power spectrum. One characteristics of LED. And the spectral width of LED types. How the spectral, here coming to this laser, when we are comparing the laser beam output, we are getting very sharp narrow beam output only in laser, but in LED we are getting the very wide output. Wide output means the intensity is very less. Okay, na? We are not transmitting this LED light into over the longer distances. Coming to the laser, we have to transmit that laser beam output, we have to coherent output. Okay, na? This is non-coherent output. Okay, this is spectral width of LED. The width is, that is edge emitting diode LED. The output this is, and this is surface emitting LED output. This is wavelength. How much of that wavelength and wavelength is there of the particular LED. Coming to that comparison of SLED, that means surface light emitting LED and edge light emitting LED. Okay, na? Here coming to the surface light SLED, that fabrication process is very easy. Coming to this ELED, it is difficult. Okay, na? Easy to, and SLED easy to mount and handle. It is difficult to mount and handle, and that is ELED. Coming to that SLED, it requires less critical tolerance, but in ELED need critical tolerance on fabrication. It is SLED is less reliable and ELED is highly reliable, and SLED is that low system performance, and ELED that is having high system performance. And coming to the SLED, less modulation bandwidth, that is having only less modulation bandwidth. ELED that is having the better modulation bandwidth of the order of the hundreds of, we are getting the modulation megahertz, hundreds of megahertz. And coming to the last one, SLED that couple less optical power into low numerical aperture fiber. I mean to that ELED that's coupled more optical power into the low numerical aperture fiber. This is about comparisons of SLED and ELED. Now coming to the advantages of LED. We know that what are the advantages of where we are using in wider applications we are using, as we are the indication purpose of and parking purpose of we are using this LEDs. Okay, na? So what are the advantages of LED? It is simple design, simple to design and easy of manufacturing, simple system integration and low cost, high reliability and simpler fabrication, simple drive circuitry, linear light output against the current characteristics. These are the main advantages of LED. And disadvantages. What are the disadvantages? The refraction of the light at semiconductor or air at interface. The refraction is, there is no refraction is there in this LED. Okay, and the average lifetime of the radiative recombination only few nanoseconds. Therefore, modulation bandwidth is limited only few hundred of megahertz, and large chromatic dispersion is there. Dispersion is, what is the dispersion? The dispersion, that is the divergence. There is some loss, that is dispersion means one type of the loss only. Okay, these are advantages and disadvantages. Coming to the applications, where we are using the industry here in LEDs are we are using in wider applications. And coming to that, if suppose in any cars are there, for the parking areas are there, and signal lights are there, we are using on that signal lights. In laboratory also we are using, and in industrial applications, some biomedical applications are also there. Applications are there for LED. Okay, with this configurations in LEDs are completed. The next topic is laser diode. We are going to discuss in tomorrow.